Some of you have been here before, I know. In fact, Mike actually showed me a picture from 9 years ago. The Friends of Guys Cliffe volunteers have done a fantastic job, because this was completely overgrown with, was it bamboo or Japanese knotweed? It was completely overgrown. So this is unrecognisable to how it was actually not that long ago. You now have something like, what is it, 300 metres? Yeah, something about 300 metres long from that end right to the other end, and we can walk along that, and we're going to make some observations. And you've got a height of, from down by one of the caves up to the top of that cliff, that's probably 35 metres or so.
Which was used as a quarry for the castle? No.
There you go. And around Warwick, this particular sandstone, we'll come on to the nomenclature in a minute, is about 80 metres thick. So approximately half the Warwick sandstone is exposed here. Is actually over 200 metres thick. So one of the questions I'm posing, I think it was in the flyer, it's even probably on here, yeah, 250 metres thick. So some of the clues are on the printouts. Is this section thinner around Warwick because that's how it was deposited, or has it been, the top, has it been eroded? And we're going to try and work that out. And one of the things we're going to do is look at the map. So this is now a geological map, and my compass tells me that north is that way. That's north, so that's west, that's east, and south. So we're going to work out which way the river, because these are river deposits, they're one particular type of river deposit. Those of you that went to Polesworth, when was that, Ray? A month ago? A month ago, last month. Those of you who went to Polesworth, which is also a Triassic river sandstone, we decided that was a particular type of river. It had lots of pebbles in it. This is a bit different. So we're going to try and work out how this is different to the Polesworth and find out what type of river this was. And the clue is in the sedimentary structures and in the types of surfaces. I'll come on to that in a minute. So the geological map, we are approximately in the middle of that big yellow blob, somewhere here. You can probably, that's it, yeah, that's it, yeah, yeah. No, that blue thing, no, I think that's, no, it's not the river, no, that's not the river. That's the unit overlying this sandstone. It's a thin unit, yeah. So the sandstone we're looking at is regionally now known as the Helsby Sandsone, and the type locality is Helsby in Cheshire. Now it used to be, back in the good old days when life was relatively simple, we used to call it the Kuiper Sandstone, and the Kuiper Sandstone was directly beneath a Kuiper marl, and Kuiper comes from the threefold division of the Trias in Germany, the type locality being near Kuiper in Germany. So you have the Bunter, the Muschelkalk and the Kuiper, and the Bunter is the sandy part of the sequence below a marine transgression, the Muschelkalk, the mussel limestone, and then the Kuiper was a gypsiferous package full of evaporites that was deposited above it. So threefold division originally, Kuiper, Muschelkalk, Bunter, and this was known to be the Kuiper sandstone because it occurs above what is known to be that mussel limestone. So the Polesworth formation we saw last month is Bunter equivalent, so it's older. So this is the Kuiper, the younger sandstone that lies above an unconformity, because the Muschelkalk isn't actually present in Britain. So that limestone that in Germany is a marine transgression is just not present here. This was higher ground. The transgression didn't get this far, at least we don't think it did. So this is the sandstone above the Muschelkalk, above this marine transgression, but beneath the Kuiper marls, which we now call the Mercia Mudstone Group. Confused? Because it was called the Kuiper Sandstone, and through the 1850s to about, I don't know, 1930, when local geologists described it, and they started calling it the Warwick Sandstone. For good reason. It's around Warwick.
I like.
Yeah, I like that too. And the geologists that worked around Bromsgrove called it the Bromsgrove Sandstone. And that happened all over the country. So the same sandstone in Devon is called the Otter Sandstone because it's near the village of Otter and the River Otter. Elsewhere it was called, well, other local names. So the BGS, bless them, then decided that was too chaotic. Because it's the same sandstone, you couldn't have different names for the same sandstone all over the country, particularly when they were making digital maps. Where would you put the boundary? So they decided in their wisdom that all these local names would now be called by one name, which wasn't going to be Kuiper, because it's not actually the equivalent of the German Kuiper, so they called it the Helsby Sandsone. So the Kuiper Sandstone, which was a regional term, became a local term, Warwick Sandstone or Bromsgrove Sandstone, and then the BGS in the 1980s said, no, we're going to call this the Helsby Sandstone. So you can now look at the same sandstone package in Cheshire, actually in Lancashire, Cumbria, all the way down to Devon, through the Midlands, and it's all called the Helsby Sandstone. Yeah, and we know that that's north. So the next thing is to start looking at some rocks. Now you're orientated, or should be, and suitably confused about what you call it. I don't care what you call it. Actually, Warwick, Bromsgrove, Helsby, I don't care what you call it. We're going to try and work out how it was deposited. Now, I was taught sedimentology by a famous gentleman who sadly is no longer with us, David Thompson, who was at Keele, and he wrote many papers on the Trias. And he took me into a quarry not dissimilar to this, and when I first looked at it, I thought, grief, how do you make any sense of that? So if you haven't studied fluvial sedimentology, this probably looks all a bit chaotic. But once you understand what to look for, there's a story. Actually, the story is relatively straightforward, but you've got to know what you're looking for. So in the cliff faces, the first thing we're going to point out are surfaces, because the surfaces are key to understanding what's in them. So I'm just going to walk over there. On this flyer, I'm going to pass this one around too. I've actually drawn on, I think it's a cliff section just over there. There you go. I've drawn on, there's one more, there we go, pass them around. I've drawn on the cliff face some surfaces, and you're going to try and get your eye in it and look for those surfaces. So, there are lots of surfaces. I'm just going to pick one out. I don't think it's going to fall on my head, I don't think. So, we're going to start with this one surface. Can I just give you those, please, Ian, for a second? Yeah, the answer's on there, but never mind. So I'm going to pick out one surface, and I'm going to choose this one to get us going. So I'm just going to walk along this surface. We call it walking stratal surfaces, and you can, if you go to Utah and do this sort of geology, you can follow these surfaces for miles. And over miles, they change in character quite dramatically. Over 300 meters, they don't change a huge amount. But let's follow this one. There it goes. It comes up here. So it's not flat. It's not a planar surface. You go up there, and then it comes down here. Down there, and then it's down there. And actually there, it converges with another surface that was here. So that surface, yeah, it's different to this surface. So that is a flatter surface. And you can see it's a break. That's a definite change in the rocks, as is this one. The character of this bit of sand is not the same as that. This one's got, we'll come to them in a minute, this one's got beds that are inclined, and they come down from up here down to the base of this surface. Yeah? So this surface has beds coming onto it. We call these cross beds, There are different types of crossbeds. This is a surface that then comes down onto this surface, such that, there it is, look, such that that bed has gone. How can that be? It's all sand. So that's another point I should make. This type of river deposit, what's the main sediment it's depositing?
Sorry, what?
The main type of sediment. It's sand. How much mud is there in this sequence? Very little. There are bits, we'll find them in a minute. There are a few bits up there if you look. Approximately, from the top to the bottom, what percentage of the sediment is mud? Less than 5%. Certainly less than 10. Yeah? Not very much. So 95% of this sequence is sand. Now for a river to just deposit sand, that's actually quite unusual. So surfaces, this one is clearly slightly undulose. This one is planar, and the undulose one cuts out this package of sand. And then this surface continues. In fact, there's a bit of mud down here, I think. That surface, we lose it down in the base of the cliff. So that's two types of surface. This one that is erosional. This one that's planar and gets eroded out. And then there's another surface here. How far can we trace that one? Here. And you can trace that a long way, all the way along there. And somewhere here, this one also starts to cut down. Yeah? And if you look closely, where it cuts down, that surface, it's got a concentration of these funny nodules. And it's on these, so this locality is also famous for finding fossil reptiles, early dinosaurs, rhynchosaurs. And they were called dirt beds, and they came from these little conglomerates of these transported units. So the place to look for dinosaur remains, skulls, bones, is on these surfaces. So there is actually, between these two, so there's one surface there, that's a top surface, and a bottom surface, and the bottom surface is erosional. Yeah? Everyone got that? And then within it there are crossbeds, inclined crossbeds. There's actually another surface here, which is not entirely obvious in there, but if you come around here, that surface is here, and it also has these nodules on it. And not present there, but present here is another unit underneath that surface. We've got another surface in here that's not entirely obvious, but I can now see it, it's here, yeah? That becomes a more significant surface. Surfaces are key. So when you look at these types of river systems, you have to look at the surfaces before you start looking at what's between the surfaces. Because the surfaces are actually the bottom and the top of the bed forms. The bed forms are the sand deposits that were in the river when the river was flowing. So they are tubes. You're right, they are tubes. We'll come back to the tubes. So the bottom of the channel, I'm calling it a channel now, it's the first time I've used that word, the bottom of this depositional unit, which I'm calling a channel, is erosional. So that tells you it's a high energy flow. For it to be eroding sand, it can't be a very quiet flowing river, it's a high energy flowing river. And it's also transporting these big things, whatever they are, which we're going to define in a minute. So that's the base of a river channel. Where's the top of it? Is it there, or is it there, or there? Any suggestions? It's that one. It's that one. Why are we saying that? I mean, you're right. Well, that's cross-bedded, but the cross-bedding in there is not the same as the cross-bedding in that unit. Because this one, look, the cross-bedding here comes down onto that surface. So this is two bed forms in the river, one above an older one. So that's the base of the channel, that's a bed form, and that's a bed form. So in this case, in these bed forms, they had a shape, they had a geometry. They were dunes underwater dunes, not aeolian dunes, we call them bars, that were in the channel whilst it was in flood and were migrating down the channel. They're in-channel bars. And in this case, you had two bars, one on top of the other. How do we know which way the river was flowing? So the answer to that is to look at the bedding within the bed forms. We're calling the bed forms bars in the river. So this is the cross bedding. That's the cross bedding. And if you find 3D surfaces, this one isn't quite 3D, but anyway, look, the way bars work, the current flows up. Who's got the crib sheets? Thank you. There we are. Yeah, Ian's got them, yeah. So here we go. Here's the crib sheet. The answer's on the piece of paper. I'll pass them around in a minute. The current flows up the backside of the bar, over the top, and then downstream. Depending on the flow of the river, you can have what's called a separation eddy in the deeper water in front of the bar, and you can get little countercurrent ripples that climb up the front face of the bar. So this is the side that the grains move up. This is the avalanche face, and the avalanche face gives you the direction of flow because the grains cascade down there. Exactly. So there you go. There's a modern example of this type of river. This one is from I think it was from somewhere in Canada, Saskatchewan. So that's a braided river full of. We're going to come to braiding in a minute, because braiding is a feature of rivers that have highly variable discharge. When the river's in flood, it's not braided because all the bars are submerged and they're moving along in the river. As the flood stage subsides and the water levels fall, the bars become exposed and create the appearance of braiding. So we're going to work out in a minute how we know if this was braided or not, because we're going to look for evidence of fluctuation in discharge, and that also means looking at the surfaces again. So let's pass that one around. You may as well have the last one as well while we're here. Sorry I didn't print out more. There we go. There we go. Share them around. And then the last one, am I going to show you that now? Why not? Yeah, I mean, I'm not going to hand this one out just now. We'll look at it though. So this is a very famous published depositional model for this type of river, and it's a 3D block model that shows the type of bed forms, the deposits you get in both cross section and longitudinal section, and it also shows the river bed with the bars underwater migrating downstream. So when you look at the longitudinal section, you see mostly cross beds. When you look at the cross section, you see mostly troughs. Anyone see any troughs in there? Right. So the upper bar is probably flowing out of the cliff because it's a cross section, whereas this bottom one is flowing to your right. So the bed forms, the flow direction changes up the sequence. That's not entirely surprising. You know, these rivers they're not meandering. They're sort of they're moving around the bars in the river. So I'm going to give you that now. Let's pass that one around too. If anybody wants a digital copy of these, just drop me an email and I'll send you the file. It's easy. There we go. There we go. Right. So which direction was the river flowing in? You get that from the cross beds. So valid for this unit. Here we've got two bars. That's the base of the channel. Bar 1, bar 2. And these are nice cross beds, so we can look at the direction of dip. Here's my compass clinometer. And these are... It is an apparent dip, which is why I mentioned 3D faces. We need to be sure what the exact direction is. You really need a 3-dimensional exposure, which there are here. But we can get I mean, there's a 3D exposure here, Ian. I can see into here, and actually that is close to maximum dip. It's clearly like that. So it is going that way. And it's in the order of, so if it's going that way, it's just shy of north, slightly west of north. So this river was flowing from the south to the north. What was the minimum water depth? The story's there, the answer's there. What was the minimum water depth? If this is a subaqueous bar, and that's its bottom and that's its top, what was the minimum water depth? That. Yeah. And this one? That. So two bars, one on top of the other, each, what are they? 25 centimetres thick? That's the minimum water depth, because you don't know how deep the water was above the top of the bar. It could have been. But in general, they're not much deeper. The water flow over a bar, if it's the bar top, is normally not that much thicker over the top. Flowing from left to right, south to north, and the water depth was 25-30 centimetres, at least.
At that point?
At this point, yeah. I mean, so if you stand back, there's some much bigger sets. They're much bigger. How deep was that channel? Look at the size of those. So the river changed in velocity, carrying capacity, and water depth. It's not all the same. So they're the troughs. So that's a different cross section through the river system. That's right. So these are flowing out of the cliff. Yeah. Actually, they could be flowing into the cliff. You need to work that out by measuring the dip on those trough cross sets. So at times the rivers were in flood and erosional, and at times they weren't. They were flowing around, and we're going to find an example of reactivation in a minute. Because when the water levels drop, the sides of the bars get reworked, and we call that reactivation. So can we say anything about the size of the bars? How big laterally were the bars? Can we say anything about that?
Sort of 7 or 8 metres there.
Well, so that one, we can trace it from beyond Gareth. It is there all the way, and you can do this exercise by taking photographs. So that bar carries on, and actually you lose it here. So how wide is that one? So this one was at least, what's that, 50 metres? And it's eroded out, so it's at least 50 metres long or wide. It's long actually in this case because it's a longitudinal section.
Is there any indication that the river dried up? Another fault here?
There is. So back to the nodules. These are roots. So the roots were growing in the bar to get vegetation, and because they're vertical and we can measure them around the corner, some of them come down by more than a metre. So the roots are at least a metre long into this sandbar, searching for water. So to get a plant that's got a root that's at least a metre long, they're quite big plants, yeah? They were probably conifers. And that means for a plant to grow to such a height that it had roots a metre long, that's taken some time to grow. How long do your conifers take to grow in your garden? It's
5 years.
5-10 years, yeah. So you know, because they were vegetated with roots, that they were stable for at least 5-10 years. Yep. And they were eroded because the concrete, in fact, you even had to have time, not just for the trees to grow, you had to have time for the calcite concretions to grow around the roots, and that takes longer. That actually takes probably hundreds of years.
Were plants growing suggested more organic material in the riverbed than 5%?
Funny you should say that, because, well, no, it's the muds that's 5%.
Yeah.
But some very famous palynologists have devoted their life to studying the Trias. So one such gentleman with the BGS, now retired I think, Jeff Warrington, has crawled all over the Trias in Britain and elsewhere looking for plant spores. And that's basically how we date some of this stuff, because there are very few fossils. And in the mudstones, he has collected plant spores, and so we know what type of plants were growing. And there were cycads, conifers, very early gymnosperms. There was quite a varied vegetation at the time, but so little of that is preserved because this was a desert, and the reason why the rocks are white or reddish coloured is because they were oxidized. So much of the organic matter outside of the mudstones is oxidized. It's just gone. It's exposed to surface temperatures back in the Trias. I mean, we're worried about global warming now. We know because people have studied fluid inclusions in these Triassic deposits, not from here but from elsewhere. We know surface temperatures back in the Trias reached 60 degrees centigrade. It was pretty hot. Well, they died out from time to time because then modern cycads would struggle. I mean, they like very humid, moist, wet environments. So there's another unit of sand, the base of which Max has just pointed out has a series of quite large holes on it, and that goes all the way. There's a change there, but it then goes up to that next break. So the next river channel also has two bars in it, and this one, the overlying one, actually erodes down there, and then the overlying one is probably a metre or more in thickness, and there's lots of troughs. So this orientation was coming out of the cliff section. Why have we got holes along the base of the channel? That's because it had mudstone clasts, mudstone pebbles, and they've been weathered out. In places you can actually see the mudstone pebbles still in situ. And these nodules here, they're the transported roots that were eroded out of the underlying sandbar. That's also how you know that's a large time gap at the surface. I can't tell you exactly how long it was, but I think it was hundreds of years rather than a few days or weeks. Because to create concretions takes quite a lot of time. So that's a root in situ. That one is probably two. And when you get your eye, you can start to see them coming all the way down and down here. But then these are transported. And sometimes you see them aligned on the faucets, like these here, look. They're transported. So you've got both roots in situ and transported roots. So everyone, when they first, one of the first things I said was, when I first came into a quarry like this, I thought it was chaos. I couldn't see or figure out anything other than lots of cross-bedded sand. But you can now see there's a story. And the story comes from understanding the surfaces and then what's between them. So there was one other surface that we mentioned, but I didn't give you an example of. If you remember, I used the word reactivation. When the main flood has stopped and the water levels are falling, the bars deposited during the flood become remobilized. They get reactivated. And then there's an example of that just here. So there's a nice cross-bedded bar on the left side of the cloister's cave entrance, and if you follow it along, the top of it has another little trough sitting in it, and then another one there. So they're reactivation surfaces. After the main bar had been deposited during the flood, the falling waters flowed and eroded into the top of that bar. So gap, you see the red mudstone layer, and another one just above it. So two localities here where the muds deposited during the low water stage in the depressions between the bars has been preserved. That's another good place to look for dinosaur remains on the surface between the mudstone and the sand, because that's a surface that was exposed. And if the dinosaurs walked across it, you'd find footprints there, and if they died, that's where they'd be preserved, because they wouldn't get washed along by the river. So that's a good place to look for fossils. Yeah. There's an in situ bit of mudstone. It's remarkably hard. In fact, look here. That's even nicer. Look at that. Oh, shades of Polesworth. So this is a conglomerate sitting in this erosional hollow on the. Actually, how's that got there? It comes down from this surface. So there's an erosional hollow that's full of conglomerate, most of which is transported root material. But that'd be a perfect place to look for fossils. No, it is. It's aligned on the foreset. Yeah, that's the foreset there. Yeah, it's aligned on the foreset. So don't break it off because it's triple SI and you don't get many bits of dinosaur bone. It does, and that's typical of what phosphate looks like. That sort of colour, or it could be fossilised wood. You'd need to take a thin section to be sure. I think that's a bit of Rincosaur bone.
That's the one that's in Warwick Museum.
Yeah, yeah.